In this episode, it's about OPC UA for plasma surface technology. With me today, we have Dr. Martin Riester from our VDMA Surface Technology and Christopher Lear, who is editor of several OPC UA companion specifications from the department Machine Information Interoperability. Martin, Christopher, the stage is yours. I'm excited about our information we get today from you.
Okay, thank you, Andreas, for the kind invitation to have this talk. We will share the input. Martin Riester, will talk about the working group structure and give some background on plasma surface technology machine types. And then Christopher will take over with the information model overview and giving an outlook at the end. Next slide. Yes, in surface technology, we have several working groups dealing with OPC UA, machine-to-machine communication. We started off in 2018 with coating technology for organic coating materials, meaning paint application or adhesive application. Then in 21, we started a shot blasting technology working group and the plasma surface technology group, which is focused today. And just recently, beginning of the year, we started with the fourth working group on cleaning and pretreatment technology. Next slide. The difference between these four working groups is not only the technology, but the structure or the content of the companion specifications. Coating technology for organic coating materials. These coating lines consist of several machine types, so we will have for this working group several companion specifications and also machine-to-machine communication specified in these standards, and not only machine-to-MES communication, how it is the case for most of the companion specifications. In shot blasting and in plasma surface treatment, we only deal with one machine type. Basically, we only have one companion specification and define varieties of the machine type, and we only describe machine-to-MES communication. And for the last group, cleaning and pretreatment technology, this one is similar to the first coating technology for organic coating materials, and it can actually be part of such a coating line. But this working group on cleaning and pretreatment is working on a companion specification for one machine type and covering also machine-to-machine communication as well as machine-to-MES communication. Next slide. So let's look at plasma surface technology. It's basically using plasma as a tool to treat surfaces. That's the simple description of it. You can use this plasma to activate surfaces, to clean surfaces, to etch surfaces, and you can modify surfaces by implantation of ions, like when you plasma nitride or boride a surface to make it harder and wear resistant. And you can, of course, also use it for coating. That's a more complicated process then, because then you have to bring metal ions into the plasma or carbon ions, depending on the process which you are following. But the result is that you will have thin layers on your substrate, enhancing the surface properties for wear, for tribology aspects, and so on. So the machine types we cover in this companion specification is plasma machinery, which works at atmospheric pressure, which is typically used for activation or cleaning of surfaces, but you can also deposit organic or bio coatings with that technology. And on the other hand, we have low pressure plasma machine processes or plasma processes with the physical vapor deposition or chemical vapor deposition, which are two specialized process types. Plasma nitriding is also similar. So you have a variety of processes which you need to be held at low pressure. So these two machine types differ a little bit by the layout, but are both covered in one companion specification. Next slide. We started, as I said, as core working group 3, plasma surface technology, within the Surface Technology Initiative, which VDMA, together with the OPC Foundation, conducts for this sector. We started in 2021, May, and received VDMA MII support in person of Christopher in March 23, which brought us forward so far that we are ready for publication now. So we needed a year to get everything together with this expert help, and we expect to publish the companion specification in this quarter, third quarter 24, as VDMA 4719. And on the right side, you see the group of industry members, a lot of them providing low pressure plasma surface machinery, but also two, at least, which are working on atmospheric pressure plasma machinery. So this was the overview on plasma surface technology, and now I hand over to Christopher.
Thank you very much, Martin. Then I will take over the presentation and go into detail what content we actually have in this OPC UA for plasma surface technology specification. So the first step that is always very important in the beginning of such a development is to answer the two questions that you see on the slide. So which machines should be mapped and which manufacturing processes are to be mapped in what depth. So this maybe sounds obvious, but it's very important here to answer these questions in detail and explicitly go into the details of the machines and think about what you want to map here. So if these questions are answered, then you can define your use cases that should be fulfilled by the upcoming companion specification. And I brought a list of use cases that we are fulfilling with the plasma surface technology specification. The first use case is to identify machines in a standardized way. And this is a very basic, but still very important use case, because it doesn't make much sense to standardize all the information in the machines, but the identification of the specific machines is not standardized. So the identification is an important use case at this point. Besides the identification, we want to have an overview of all the monitoring details that the machine is giving us, the monitoring of the process and the monitoring of the general machine. The third use case that we defined is to physically represent our machine and its components in the information model that we want to design here. And another use case is to monitor jobs, to bring jobs to the machine, and to handle in general with tasks from MES system to machine. The last use case I brought here is the harmonization. And as you see, I highlight this use case because in OPC UA and in the development of companion specification, this is a very important topic to harmonize with other companion specifications. So if you are developing your companion specification, then you always have to know and have to search for previous work, for other specifications that have been developed, And if there are some use cases, if there are some objects that you can implement into your companion specification, then you also should do this to not reinvent the wheel with every companion specification. So this is a very important use case, and I highlighted it here because during the presentation, I will give you an insight in how we harmonize to other companion specifications. So when the use cases are defined, then you can gather the parameters that you need to fulfill these use cases, and by that, make a parameter list for your companion specification. So at this point, I want to remind you again on the first question that I introduced my presentation with, which machines should be mapped. So as Martin already said, we have two different kinds of machines. In the plasma treatment, we have the atmospheric plasma machines and the low pressure machines. And as you can see on this picture, on this slide, there are differences between these two machines. So the low pressure machine for sure needs a chamber, a low pressure chamber to generate this low pressure atmosphere. And as you can imagine, only by this chamber, we have a lot of different parameters that are important for such a low pressure machine compared to an atmospheric machine. And we wanted to have both of these machines in our companion specification. And I will later show you how we solve this. If all the parameters are collected in the end, then you can think about how should I model the information model? How should I get these data that I collected into a semantic information model and in an understandable way, for sure. So this is the work that is ongoing in such a development of a companion specification. And before I now show you our information model and show you what we did, I want to give you an insight to a companion specification that is very important for the harmonization. And I told you the use case of harmonization is very important. And I guess most of you know the OPC UA for machinery specification, which is the base specification for the whole mechanical engineering industry. So the machinery specification is actually a companion specification that is designed by a lot of different branches of our industry, a lot of different experts from different sections. And it's solving use cases that are necessary for all of these different branches of the mechanical engineering industry. And in the machinery, you can use the so-called building blocks for specific use cases. And if you are interested in such building blocks for your specification, then you can just reference this companion specification and these specific building blocks that you're interested in into your companion specification. And by that, don't redo the work, but just use the work that has already been done. And that's exactly what we did. So if we look at the target image of the machinery, then all companion specifications from the machinery industry should be based on this OPC UA for machinery. And the example for the laser systems shows how it's been done. The laser companion specification is designed on top of the machine tools specification, which is designed on top of the machinery specification. So you can see here, the base of this is the machinery. And that's exactly what we did as well. So our plasma surface technology specification has a lot of parts from the machinery. And by that, we are also using this broad base of the machinery industry. The machinery is structured in 4 documents: the basic building blocks, process values, job management, and result transfer. And you now see the highlighted blocks that we've used in our companion specification for plasma surface technology. So we used the identification blocks. We used the use case finding all components of a machine, machinery state, the counters, and the job management. And now this should be enough of the introduction. now I want to go to the information model of our plasma surface technology information model to give you an insight in how we solved this problem in our information model. So the entry point to the information model for a plasma machine is the so-called plasma surface machine type object. And inside of this plasma surface machine type object, we put all of the objects and parameters inside that are necessary to map a general plasma surface machine. But as I told you, and as Martin also told you, there are two different kinds of plasma surface machines, the low pressure machines and the atmospheric pressure machines. And we solved this problem by designing two subtypes, the low pressure plasma surface machine type and the atmospheric pressure plasma surface machine type. So these two objects are subtypes of the plasma surface machine type. And as you know, this means that we can put everything into the plasma surface machine type that is necessary for all plasma machines. And if there are some special parameters or special components in a low pressure machine, then we put these special components inside of the subtype for the low pressure plasma surface machine type. And by that we can design all of the different machines that we want to map in this companion specification. So on the following slides, I will build up now the plasma surface machine type and explain you the single blocks that we've implemented here. I don't go into the details of the subtypes because this would be too long then. But just to give you an idea how we structured our information model, the plasma surface machine type is enough. On the first level of the plasma surface machine type, we have implemented an identification block, a components structure, a monitoring structure, the machinery operation counter, machinery lifetime counter, and a job management block. So all of these blocks have specific information, specific parameter inside. And now I will give you an insight to each of these blocks, starting with the machine identification type. So the machine identification type is a building block from the machinery specification, and it's handling all the identification of a machine. So in the gray box, you see all the variables, all the properties that are inside this machine identification type. So we have a manufacturer URI, we have a model, hardware revision, software revision, but also important information like the year of construction, the month of construction of my machine, or the initial operation date. So as you can see here, the machine identification type is providing a lot of possibilities to exactly give identification information for my machine. What is maybe also important to say here, the machine identification type has three mandatory properties. So the manufacturer and the manufacturer URI and the serial number are properties that have to be given if you implement this machine identification type. Everything else that you see here in this box is optional, and by that you don't have to fill out this information. But if you want to be precise, then you can. So this is everything I would like to say now to the identification block. And by that we go to the next block, the components. The components is kind of a structural folder, and it's also a building block from the machinery. And it's fulfilling the use case to finding all components of a machine. So the idea is to put the machine components type inside of your information model, inside of your machine on the first level, and put all the components of this machine inside of this component structure. And the idea behind that is to make it easy for MES systems to make it easy for anybody who don't know the companion specification for plasma surface machines to find all the components of a specific machine. So as you know, if there's an MES system want to know the components, it just has to browse into this information model and just searching for the machinery component folder, and then it will find all the components. So that's the idea. And here on the right side in the box, you see these passages of the machinery specification. Yeah, I made some screenshots of this section. Okay, that's the machine components type. And the next here in line would be the folder monitoring, but I skipped this. I will come back to this later. And we will have a look on the next block, the machinery operation counter type. The machinery operation counter type is also implemented from the machinery specification, and it's a typical counter. So all of you know it. If you have a machine, then sometimes there are some things you have to count. And with the machinery counter, you can solve these problems. So the machinery operation counter has 3 properties. And these are the power on duration, the operation duration, and the operation cycle counter. The power on duration is representing the duration that the machinery item has been powered. The operation duration is representing the time that the machinery item has been powered and is actively performing something. So in this case, plasma treating a part. And then the third property is the operation cycle counter. So I'm not an expert for plasma surface technology, but you are. So you can define what is a cycle for my machine, and then you can count these cycles. So this is what you can do with this operation cycle counter. So these are the properties that you can find underneath the machinery operation counter type. The next block is the machinery lifetime counter type, and the machinery lifetime counter type is also a counter, but it's counting somehow on a different way. For explanation, I brought an example here. So you can, for example, solve a time that you want to count, a deadline that you want to count, or a specific time until your major inspection here in this example with the machinery lifetime counter. So it works like this. You have a few properties underneath your lifetime variable. And these are the engineering units, the start value, limit value, and indication. So these are the important properties here. And if you, for example, want to count down 365 days, because your machine has to get a major inspection after 365 days of running, then you can use this lifetime counter by filling the engineering unit with day, filling the start value with 365, and the indication with 0. And then your lifetime counter is counting down from 365. And in this example, it is at the moment at 120 days. And if it's reaching the limit value, then it will give you a notice, okay, soon you have to make your major inspection. So this is a typical use case for the machinery lifetime counter. But you can also use it for other use cases like counting how many parts I've already plasma treated. So if you say after 1000 plasma treatment cycles, I have to make a major inspection, then you can do this as well with this machinery lifetime counter. Okay, let's get to the last block that we see here. It's the job management block. And the job management block is also a machinery building block. And this is actually a complex building block that is handling all of the information, all of the processes that you need for managing a job on a machine. So in this specification, there's defined how to transfer a job from an MES system to your machine, how to get back the data from the machine to the MES system. So it's describing how to exchange the data. And it's also describing and defining what data should be exchanged. So we have a job order that is represented here. We have a job result that is defined here. So all the information that are needed to give to the information and to get back from the machine after the job is done. And then there's also a job state machine that is giving you information about the state of each job. So I will not go into detail here because this is a complex topic, but we've implemented here the job management type, and by that the user of this companion specification can easily access the functionalities of the job management. Okay, so now we had a look at this first level here of the information model, but we skipped the monitoring folder. And the monitoring folder is also a structural folder here to have a place where to put all the parameters that are necessary to monitor the whole machine. Okay, let's come to the second level of this information model. And now, as you can see, there are some nodes in the component structure and in the monitoring structure. I start with the component structure. So as I told you, the machine components type is a structural folder to collect all the components of a machine. And here we put the objects of this plasma surface machine that are needed for all plasma surface machines. So we have an object for the plasma generator. We have an object for the precursor system, an object for the gas system, and an object for the plant cooling system. So these are components that are needed for, or that can be needed for every plasma surface machine. Doesn't matter if it's a low pressure machine or an atmospheric pressure machine. I cannot go into detail for all of these components, but soon I will give you an insight to the plasma generator to give you an idea of how we structured each components of this specification. The monitoring folder I just explained to you is for basic parameters, basic variables. And in here you find some variables that are needed for the whole plasma surface machine. So we have the main switch on variable, power consumption, and substrate temperature. So this is what you can find here in our information model inside of these structural folders. One additional information here that is also very important whenever you use the building blocks from the machinery specification, then you need a machinery building blocks folder. And this folder is also a folder that is structuring all the building blocks that you've implemented into your companion specification. So as you see, this folder is also on the first level of our information model, but it has additional references to each machinery building block that we've implemented here. And I can also explain you why this is the case. The idea is, again, if the MES system, for example, don't know the companion specification for plasma surface technology, then it can still easily access all the information that are implemented here according to the machinery specification by just browsing inside of the information model for the machinery building blocks folder. And from this point on, this MES system with no knowledge of the companion specification for plasma surface technology can access all data that are implemented from the machinery specification. What are actually, as you can see, a lot. Okay, so this is the basic information model of a plasma surface machine. And as I promised you, now we have a short insight into the plasma generator. So we have now a short insight to one of the components and the type definition of one of these components. So now you can see I've added the reference has type definition. So now we have a look into the plasma generator type. And the plasma generator type has on its first level, again, an identification block, but not the machinery item identification, but the machinery component identification type. The machinery component identification type is somehow similar to the machinery item identification type, but there's a slightly difference. So we have one variable missing. It's the location variable that is added here for the machinery item identification type. And we have an additional property here, and it's the device revision. So besides these 2 points, this block is actually similar to the machinery item identification type. And underneath this, you also see here a structural folder called monitoring, because we wanted to have all the variables that are there for monitoring purposes into this folder. And as you can see now, there are a lot of parameters, a lot of information that such a plasma generator is giving you. And it's a complex component, so it needs a lot of variables to monitor, to control, and so on. So we have variables about the evaporator component, about the magnetron, the bias. We have information about the generator. We have information about the plasma and its pulse frequency. And we also have a variable for the reverse power. So information, additional information, what data types do these variables have, and so on, you find in the published document, in the companion specification document. And so also explanations about all of these variables, what they are actually representing. So this is the inside of the plasma generator type. And by that, I think you had a good insight to the information model. The persons who listened closely in my presentation noticed that we didn't talk about the machinery state block that we've also implemented in our companion specification. And I want to explain you why. As I showed you, we have 2 subtypes of the plasma surface machine type, and the working group said that the state machine for these subtypes are differently, and that's why we put the state machines inside of the subtypes of this information model. And to fulfill the needs of the working group, we also extended this machinery state machine a bit. I show you how the original state machine looks like. It has 4 states. So this is the machinery item state machine with 4 states. First state is not available, which is representing that the machine is not performing any activity. It's turned off. It's not reachable. It's turned off or in the energy saving mode, for example. Another state is the out of service state, what means that the machine is actually reachable, but it's not working because of something is broken or it's blocked in the process, something like this. Then another state is the not executing state, what is giving you the information that your machine is completely fine. It could work, but for any reason it is not working. For example, there's just nothing to do now, or your machine is waiting for another machine in the line. And then we have the state executing, and for sure this state is giving you the information that in our case, the plasma surface machine is plasma treating a part or a surface. Okay, and we've slightly extended these state machines in our specific subgroups. So the low pressure surface machine extended the not executing state by vented and standby. So these are two states that are different here because we have the pressure chamber, the low pressure chamber. And if the low pressure chamber is opened, then it's in the state vented, but in the not executing state. And if it's closed and the low pressure is built up, then we are in the standby mode. And the atmospheric pressure state machine has also two substates of the not executing state, which are idle and standby. So these are the machinery item state machines that we've implemented in our component specification for plasma surface technology. Yeah, here you see again an overview of our companion specification information model. And as all of you know, this is just the basis of your information model. So if your machine is generating more information, then you can just easily add them to this information model and still be completely fine with this companion specification. You also have the possibility to not implement only one component. You can have 3 gas systems, 4 gas systems, or 5 plasma generators. So it's absolutely fine to add here more components by using our defined component types. So this is everything I have to say for now to our information model, to our information structure. And as you see, we are very far. We are done with the information modeling. We are done with the content work. And now the only thing we have to do is publish our companion specification. And as Martin already said, we will publish it very soon. And if you're here in this live presentation, then you cannot access this information model, this companion specification on our database now because it's not uploaded yet. But if you're listening this presentation recorded, then it should be already uploaded into this database. So this database you can find on the website of the VDMA. It's our database for companion specifications. And here you find a link on this slide, and you can easily access all of the published companion specifications of the VDMA. It's free of charge. You don't have to sign up or anything. And by that, it's very easy. Okay, so this is everything I have to say to our working group. Thank you very, very much for your attention. And with this, I would like to hand over to Andreas again.